Hello everybody, today I'm going to explain the first problem of the 2024 December contest in the Gold Division, the problem Cowdependence. And in this problem we are given n cows and we know for each cow its label from 1 to n, and we want to find out for every possible size of a group, where a size of the group is the maximum distance between the first and the last cow we are allowed to have, to find the minimum number of groups that could have been formed. And now, obviously, when we think about it, we want to be able to avoid having a brute force algorithm, because that would be very bad for our prospects in terms of time complexity, while also being able to uh, do it optimally. And if we look at the subtasks, we have two distinct types of subtasks besides the ones for small n. We have a subtask where there are few distinct values, and we also have a subtask where everything shows up very few times. And if we can, for these kind of problems, when you see two different types of restrictions, if you see that if you can find a solution for each of the two types of subtasks, then you are basically set for the entire problem solution, because the optimal solution consists of solving both of these subtasks optimally. And let's take actually each subtask in turn. So for the subtask when no label appears more than 10 times, you can think in terms of you know that you will have at most 10 groups with that value at the beginning, and because of that reason you can think that for each starting point you can see how much you can expand your group at the initial step, and you will only have roughly 10 squared different points of interest that could interest you during the entire process of these groups. So basically, we only care about each pairwise difference between two values, and basically we can do some sort of a brute force, maybe with some difference arrays, and just find the answer like that. For the subtask where everything is up to 10, when you think about it, we can start by considering the first few moves. And if you know that the values show up many times, after a certain number of moves, the number of groups reduces dramatically. If you think about it, if you have a length of the group equal to square root of n, the number of groups can be at most square root of n. And this is already where things actually start getting easier from this regard, because you will have fewer groups, and it's getting easier and easier to process them in a very similar manner to what we did for the tests 8 to 11. And basically this is what I ended up doing to end up getting the full solution. And I combined simply the observations I made for these two subtasks, for 7 and 811. And I ended up coding this in a rather smooth manner. As you can see that the times haven't been too large. So let me show you the code. So first off, I kept for each number the positions where it shows up. Obviously, if it doesn't show up anywhere, we don't do anything. Otherwise, I processed using brute force the first 50 moves. So this is something I did for every group, to just process 50 moves. The overall complexity of this part of the code is 50 times n, because the sum of the sizes for all of the groups is n. So we have 50 times n, nothing too dramatic here. And we want to see after 50 steps, how many points are still relevant. And the number of points subtracts dramatically. Probably I could have gone even for a higher number, 100 then or 200 then. I think it's optimally to go like square root of n, but this is actually what I managed to make it work in the contest. So then we want to see the configuration after this given step. And then in order to optimize the process, I am going to use something I explained earlier for the subtask with few occurrences, something which is to basically find out the smallest difference between two beginnings of a group, because when we get a bigger size of the group, it will be that we can merge two different starting points and have them part of the same group. So basically by doing this, we skip through a lot of steps without having to compute it over and over for every value from 1 to n. And when we know the new size we are going to test this as, we will binary search for each starting from the beginning of the group, where can that group end, and then we will do the same for the second, third group, and so on. So basically, because we did brute force the first few group sizes, this part of the code is going to be very fast. As we get fewer points, we will have fewer things to check, and also the points will also merge. And in order to keep track of the answers, I kept a difference array where at first I just added for everything the number of groups we have at the beginning, and then I increasingly subtracted, as you can see here, and then at the end I just added everything up to get to the answer. For this kind of problems, it's very important to think how to combine two or multiple solutions, and this is something you see a lot even in square decomposition when you think about it. Basically, having a relatively small number of cows, or numbers like 10 to the 5 here, and basically just from there making sure to get the answer done and maybe combine both solutions in your favor. If you enjoyed watching this video, please like the video, subscribe to the channel, and if you have any suggestions or feedback, please leave them in the comments. I am very delighted to hear your thoughts, and if you have any other questions, please also address them there. If you or someone you know is interested in working more closely with me towards the USACO or competitive programming journey, please check out my website for ways to contact me so that we can work on a more exclusive basis as part of my tutoring program. And until the next time, good luck for the next contest. Happy holidays, have a great upcoming year, and see you next time. Cheers.